In 2022, physicists announced they had created a wormhole. The announcement made international headlines. Major newspapers ran the story. The paper was published in Nature, one of the most prestigious scientific journals in the world. The research was conducted on Google's quantum computer. The scientists involved were from Caltech, Harvard, MIT, and other leading institutions. It was not a wormhole. No shortcut through space was created. No tunnel connecting two distant points in the universe was opened. No physical object passed through anything. The quantum computer performed a calculation. The calculation modeled some mathematical properties of a theoretical wormhole in a specific simplified model of quantum gravity. That is what happened. That is the full story. But here's what is interesting about the 2022 story and why this video exists. The gap between what was claimed and what was done is not a story about scientific fraud or media incompetence. It is a story about how genuinely confusing the physics of wormholes has become, about how the boundary between a wormhole that exists in mathematics, a wormhole that exists in quantum information, and a wormhole that exists in physical space has become so blurred that even physicists disagree about where the lines are. Because of a conjecture published in 2013 that is one of the most profound and most controversial ideas in contemporary physics. A conjecture that says, with serious mathematical backing, that every pair of entangled particles in the universe is already connected by a wormhole, that the quantum entanglement between any two electrons, any two photons, any two particles anywhere in the universe is geometrically equivalent to a wormhole connecting them. If that conjecture is correct, wormholes are not exotic. They are everywhere. There are wormholes connecting particles inside your body right now. The question is not whether wormholes exist. The question is whether they can ever be made traversable, made large enough and stable enough for anything macroscopic to pass through. And the answer to that question involves four separate physical problems, each of which is severe on its own. Together they constitute what may be the most comprehensively obstructed theoretical idea in the history of physics. There is also something specific in the fifth section that most popular accounts of wormholes never mention. The argument that comes not from exotic matter or stability, but from quantum field theory applied to the wormhole throat itself. An argument that produces a barrier that appears regardless of whether you solve all the other problems. It is the argument that most physicists who work on this find the most decisive. That is in section 5. Everything before it establishes why wormholes are theoretically permitted and practically impossible. Everything after it explains what we learned by failing to build one. Stay with me. The logic breaks early and breaks completely. Space has a distance between any 2 points. This is the most basic geometric fact about the universe. If you want to get from here to there, you have to cross the distance between them. You can travel faster or slower. You can take a curved path or a straight path, but you cannot avoid the distance. The distance is a property of space itself, the fabric of the universe, and it is, at first glance, unchangeable. General relativity changed the first glance. Einstein's theory of gravity is a theory of space-time geometry. In general relativity, space is not a fixed background. It is a dynamic fabric that bends, curves, and stretches in response to the distribution of mass and energy. Massive objects warp the geometry of space around them. Light follows the resulting curved geometry. Time passes at different rates in different gravitational environments. And in 1935, Einstein and his colleague Nathan Rosen showed that the same equations that describe all of this also permit something else. Something that was not sought, not expected, and not immediately taken seriously. They showed that the field equations of general relativity, the equations that correctly predict black holes, gravitational waves, the expansion of the universe, and every other phenomenon of general relativistic gravity that has been tested, also permit solutions in which two distant points in space are connected by a tunnel, a shortcut, a topological connection that allows passage from one region of space to another without crossing the distance between them. This is the Einstein-Rosen bridge, what we now call a wormhole. The mathematics is correct. The solution exists. The field equations permit it. And then reality imposes its requirements. The list of requirements for a traversable wormhole, a wormhole large enough and stable enough to allow a physical object to pass through, turns out to be a list of physical demands that each, individually, strain the limits of what is known to be possible. Together, they constitute a set of conditions that may be physically unrealizable. This video goes through what wormholes are, what the physics requires for them to exist and to be traversable, what has been proposed as solutions to each of the requirements, and what the honest current assessment of whether wormholes could ever be used for travel actually is. There is something in the fifth section of this video that most physicists who work on this problem describe as the most decisive argument. Not the exotic matter problem, though that is severe. Not the stability problem, though that is real. Something that follows from combining quantum mechanics with the geometry of wormholes in a way that produces a result most people have not heard about. That result is in section 5. Stay with me. The logic breaks early and often. Before we go further, the Einstein-Rosen bridge was discovered in 1935. For decades, it was considered a mathematical curiosity with no physical relevance. In 1988, Kip Thorne, who later won the Nobel Prize for gravitational wave detection, published a paper arguing that traversable wormholes might be physically possible. Drop a comment. Do you think wormholes will ever be demonstrated to exist? Yes, no, or it depends on what physics we discover. Let's start with the geometry. Because wormholes are fundamentally a geometric concept, a statement about the topology of space, and understanding the geometry is essential to understanding both why they are interesting and why they are difficult. In everyday experience, space has a simple topology. Between any 2 points, there is a path of minimum length, the straight line, or its curved equivalent in the presence of gravity. The geometry of space determines how long this shortest path is. Now imagine taking a sheet of paper and marking 2 points on it, one on the left edge and one on the right edge. The shortest path between them crosses the paper. If the paper is flat, the path is a straight line. If the paper is curved, bent into a U shape, the points can be brought closer together, reducing the path length between them. Now imagine folding the paper so that the 2 points are directly above each other, nearly touching, and then punching a hole through both layers of paper, connecting the 2 points with a tunnel. The tunnel is shorter than the path that crosses the paper's surface. An object that enters the tunnel on one side emerges from the other side without having crossed the paper. This is a wormhole, in 2 dimensions. In the actual 3-dimensional space of the universe, the analog is a tunnel connecting 2 regions of 3-dimensional space, possibly regions that are far apart in terms of the distance that would have to be crossed traveling through normal space. The mathematical structure of a wormhole is a handle, a topological feature that connects 2 otherwise separate regions. The simplest wormhole geometry, the Schwarzschild wormhole, or Einstein-Rosen bridge, appears in the maximal extension of the Schwarzschild solution to Einstein's field equations. The Schwarzschild solution describes the space-time geometry of a non-rotating black hole. When the full mathematical extension of this solution is analyzed, the maximal analytic continuation, which was worked out by Kruskal and Sekerez in the 1960s, it turns out that the solution describes 2 asymptotically flat regions of space connected at a throat. The Kruskal-Sekerez diagram shows that the Schwarzschild solution contains 2 exterior regions, 2 separate sheets of space-time connected by a wormhole. An observer in one exterior region cannot communicate with an observer in the other. The connection exists geometrically, but is not traversable. Anything that enters the wormhole from one side is pulled toward the singularity and destroyed before it can emerge from the other side. The Schwarzschild wormhole is not traversable. It is a geometric connection that exists in the mathematics, but cannot be used as a shortcut by any physical object. For a wormhole to be traversable, for it to actually allow passage from one region to another, additional requirements must be met. The wormhole must be large enough to allow passage. It must be stable. It must not collapse before the traveler can complete the transit. And the matter and energy threading the wormhole must be of a specific type. It is this last requirement that is the most problematic. The Kruskal-Sekaris coordinate system, developed independently by Martin Kruskal and George Sekaris in 1960, provides the maximal analytic extension of the Schwarzschild solution and makes explicit the two-sheeted structure of the spacetime, the existence of two exterior regions connected by the Einstein-Rosen bridge. The bridge was originally described by Einstein and Rosen in their 1935 physical review paper, The Particle Problem and the General Theory of Relativity, though they interpreted it as a model for elementary particles rather than as a potential space-time shortcut. The interpretation as a tunnel connecting two regions of space was developed later by Wheeler, who coined the term wormhole in 1957. To understand why traversable wormholes are physically problematic, you need to understand the energy conditions of general relativity. General relativity describes how matter and energy curve spacetime. The relationship between matter energy and spacetime curvature is given by Einstein's field equations. But the field equations themselves do not specify what kind of matter and energy can exist. They accept any matter-energy distribution as valid input. The energy conditions are additional constraints, physically motivated requirements that restrict the class of matter-energy distributions that are considered physically reasonable. They are not derived from the field equations. They are imposed based on our physical understanding of matter. The most important for wormholes is the null energy condition. The null energy condition states that for any null vector, any vector pointing in a light-like direction in spacetime, the energy momentum tensor contracted with that vector must be non-negative. In simpler terms, no matter how you look at it, the energy density of any physical field or substance must be non-negative. The null energy condition is satisfied by all known forms of matter and energy. Ordinary matter, positive energy density. Radiation, positive energy density. The electromagnetic field, positive energy density. Dark energy, also positive energy density, despite its repulsive gravitational effect, because the energy condition is about energy density, not about the sign of the gravitational effect. In 1988, Morris and Thorne published a paper in the American Journal of Physics, written to be accessible to undergraduate physics students, that established the requirements for a traversable wormhole. Their analysis showed that for a wormhole to be traversable, to remain open long enough for something to pass through, the matter threading the wormhole must violate the null energy condition. The throat of a traversable wormhole must be threaded by matter with negative energy density. Not just any matter. Matter that has energy density less than zero. Matter that, in a sense, has less energy than empty space. This is not obviously impossible. The Casimir effect, the attraction between two closely spaced metal plates in a vacuum, is associated with a region of negative energy density between the plates. The quantum vacuum, pressed between the plates, has lower energy than the vacuum without the plates. The energy density is genuinely negative. The Casimir effect is measured in laboratories. Negative energy density is a physical reality at small scales. The problem is the scale and the amount. For a wormhole that a human being could traverse, say, a wormhole with a throat radius of 1 meter, The amount of negative energy required and the precision with which it must be distributed around the throat is extraordinary. Ford and Roman, in a series of papers in the 1990s, derived quantum inequalities, constraints on the magnitude and duration of negative energy density regions in quantum field theory. Their results showed that negative energy density can exist, but is subject to severe constraints on how large it can be and how long it can last. A traversable wormhole of macroscopic size, large enough to be useful for travel, would require negative energy in quantities far exceeding what quantum field theory permits in the form of Casimir-type effects. The gap between the amount of negative energy available through known quantum processes and the amount required for a macroscopic traversable wormhole is enormous. This does not prove that traversable wormholes are impossible. It demonstrates that the matter required for them is not available from any known source. It would require exotic matter, a form of matter with macroscopic negative energy density that has no confirmed existence. The Morris and Thorne 1988 paper, Wormholes in Spacetime and Their Use for Interstellar Travel, a tool for teaching general relativity, in the American Journal of Physics, was written in response to a request from Carl Sagan, who needed to know whether wormhole travel was consistent with known physics for his novel Contact. The paper established the exotic matter requirement and analyzed the constraints on tidal forces and traversal time. Ford and Roman's quantum inequality papers, published in Physical Review D in the 1990s, showed that negative energy density is permitted by quantum field theory, but is subject to constraints that make the construction of macroscopic wormholes extremely difficult, if not impossible, using known physics. Let's assume, for the sake of analysis, that the exotic matter problem is solved, that somehow macroscopic negative energy density can be produced and maintained around the throat of a wormhole. The next problem is stability. The Schwarzschild wormhole, the Einstein-Rosen bridge of the non-rotating black hole, is not just non-traversable, it is dynamically unstable. It pinches off, collapses to zero throat radius, in the instant it forms. Even a photon entering the wormhole cannot complete the transit before the throat closes. This instability is not specific to the Schwarzschild case. It is a general feature of wormhole solutions without exotic matter. The gravitational attraction of the wormhole's own geometry causes the throat to contract. Without something to resist this contraction, without a repulsive force acting at the throat, the wormhole collapses. The exotic matter is supposed to provide this repulsive force. Matter with negative energy density gravitates repulsively. It pushes space apart rather than pulling it together. The right distribution of exotic matter at the throat would provide the pressure needed to hold the wormhole open against its gravitational tendency to collapse. But the stability of the resulting configuration, a wormhole throat held open by a shell of exotic matter, is itself not guaranteed. Small perturbations of the exotic matter distribution could trigger either collapse or runaway expansion. The stability of specific wormhole configurations has been analyzed in the literature with mixed results. Some wormhole configurations are shown to be stable against small perturbations in specific models. Others are shown to be unstable. The general answer depends on the specific wormhole geometry, the equation of state of the exotic matter, and the nature of the perturbation. There is an additional stability concern specific to traversable wormholes, one that is separate from the structural stability of the wormhole geometry. A traversable wormhole, as Thorne noted in his original analysis, is a potential time machine. If one mouth of the wormhole is accelerated to relativistic speeds relative to the other, time dilation creates a temporal offset between the two mouths. A wormhole that is initially just a spatial shortcut becomes a time machine. And as we discussed in the video on closed time-like curves, Hawking's chronology protection conjecture predicts that quantum effects will destroy any CTC region before it can form. Applied to a wormhole-based time machine, this means that as the temporal offset between the wormhole mouths increases toward the value at which the wormhole becomes a time machine, Quantum vacuum fluctuations accumulate near the wormhole throat and produce a divergence in the energy momentum tensor that destroys the wormhole. The wormhole is not just unstable against small perturbations, it is potentially destroyed the moment it is used as a time machine, which any relativistically moving mouth would eventually make it. The stability problem, combined with the exotic matter problem, creates a picture in which a traversable wormhole is extraordinarily difficult to create and extraordinarily difficult to maintain even if created. The dynamical instability of the Schwarzschild wormhole, its tendency to collapse in zero proper time, was first analyzed systematically by John Wheeler in the 1950s and formalized by Fuller and Wheeler in a 1962 physical review paper. The stability of wormholes threaded with exotic matter against small perturbations has been analyzed by multiple authors. Hochberg and Visser, 1998, showed that wormholes satisfying all traversability conditions are generically unstable unless the exotic matter has specific properties, while Kim and Lee, 2001, found stable solutions in specific models. The general result remains model dependent. Stop here. A traversable wormhole requires exotic matter with negative energy density. The Casimir effect produces negative energy density, but in amounts that fall far short of what a macroscopic wormhole would require. If you could choose one physical law to change in order to make wormholes possible, one constraint to relax, which would you choose? The null energy condition, the quantum inequalities on negative energy, or something else entirely? Drop your answer below. Now let's talk about the development that has made wormhole physics most exciting in the last decade and most confusing. In 2013, Juan Maldacena and Leonard Susskind published a paper with the title Cool Horizons for Entangled Black Holes. The paper proposed a conjecture that has become known as ER equals EPR. EPR refers to Einstein, Podolsky, and Rosen, the three authors of the 1935 paper that introduced quantum mechanics entanglement as a paradox, arguing that quantum mechanics was incomplete because it allowed apparently instantaneous correlations between distant particles. The EPR paradox was eventually resolved, not by showing that quantum mechanics was incomplete, but by showing that the correlations are real, but cannot be used for faster-than-light communication. ER refers to Einstein and Rosen, the same 1935 paper that introduced the Einstein-Rosen bridge, the wormhole. Two papers published in the same year by the same first author, describing two apparently completely different physical phenomena. Maldacena and Susskind propose that they are not different, that they are the same. The ER equals EPR conjecture proposes that quantum entanglement between two systems is equivalent to a wormhole connecting those systems. Two entangled particles are connected by a wormhole. The wormhole is not a large, traversable tunnel. It is a quantum geometric connection, a feature of the quantum geometry of spacetime that corresponds to the entanglement between the two systems. This conjecture emerged from the analysis of the black hole information paradox, the conflict between quantum mechanics and general relativity that we discussed in the video on black hole singularities. In the context of the firewall paradox, Maldacena and Susskind argued that the resolution of the paradox required identifying the entanglement between the Hawking radiation and the black hole interior with a wormhole connecting them. The ER equals EPR conjecture, if correct, implies that wormholes are not exotic constructions requiring extraordinary amounts of negative energy. They are ubiquitous. Every pair of entangled particles in the universe is connected by a wormhole. The wormhole is just not traversable in the ordinary sense because the quantum wormholes connecting entangled particles are too small and too quantum mechanical for any macroscopic object to pass through. But the conjecture also suggests a possible route to traversable wormholes. If entanglement produces wormholes, then sufficiently entangled systems might produce larger wormholes. The question is whether the entanglement required for a traversable wormhole can be generated by any physical process. In 2022, Jafaris, Zlokapa, Lycan, and colleagues published a paper in Nature describing a quantum simulation of a traversable wormhole protocol on the Google Sycamore quantum processor. The paper reported that information could be transmitted through the simulated wormhole, that a signal sent into one simulated black hole emerged from the other, consistent with the theoretical prediction for information transmission through a traversable wormhole in a specific quantum gravitational model. The paper was widely reported as demonstrating a wormhole. It was not. The simulation was a quantum computation that implemented a mathematical model of a wormhole. No actual spatial shortcut was created. No actual wormhole existed in physical space. But the simulation confirmed that the theoretical framework, the coupling of two entangled quantum systems to create a channel for information transmission, works as predicted. It is a proof of concept for the quantum information aspects of traversable wormholes in specific theoretical models. The gap between this quantum computational demonstration and a physical wormhole that could transmit a macroscopic object is vast. But the ER equals EPR framework suggests that the connection between entanglement and wormholes is deep and real, and that understanding one will illuminate the other. The Maldacena and Susskind 2013 paper, Cool Horizons for Entangled Black Holes, was published in Fortschritte der Physik and proposed no single objection is absolutely decisive, but the combination of objections creates a situation in which every proposed solution to one problem creates a new problem, and the remaining parameter space for physically realizable, traversable wormholes, if it exists at all, is extraordinarily narrow. Start with the exotic matter requirement. A traversable wormhole requires matter that violates the null energy condition. The null energy condition is satisfied by all known forms of matter and energy. Violations are permitted by quantum field theory, the Casimir effect being the primary example, but are subject to quantum inequalities that limit the magnitude and duration of negative energy regions. The quantum inequalities are the decisive constraint. Ford and Roman showed that the negative energy required for a macroscopic traversable wormhole exceeds what quantum field theory permits by many orders of magnitude. This does not prove that exotic matter in the required amounts is impossible. Quantum field theory in curved spacetime may have loopholes, but it establishes that the required exotic matter is not available from any known physical source. Now consider proposed solutions to the exotic matter problem. String theory, which may modify the energy conditions in specific regimes, has been suggested as a possible source of exotic matter. Some string theory solutions do violate energy conditions that general relativity treats as fundamental. But string theory has not produced a specific, concrete mechanism for generating the required amounts of exotic matter for a macroscopic wormhole. The ER equals EPR framework suggests that quantum entanglement already generates wormholes, but these wormholes are quantum and microscopic, not macroscopic and traversable. Making them traversable requires a specific coupling between the two entangled systems that, when implemented, generates negative energy in the required configuration. The coupling required for traversability is related to the same exotic matter problem. It does not circumvent it. Now consider the stability. Even if exotic matter were available, the resulting wormhole configuration must be stable. The stability analysis depends on the specific model of exotic matter used. Some models produce stable wormholes, others produce unstable ones. Without a confirmed model of exotic matter, the stability question cannot be definitively resolved. And then there is the quantum argument, the one I mentioned in the introduction. Quantum field theory in curved spacetime, the framework used to analyze Hawking radiation and the behavior of quantum fields near black holes, makes a specific prediction about the quantum state of fields in and around a wormhole. The prediction involves quantum correlations between the two mouths of the wormhole. The specific prediction is this: For a wormhole to be traversable in the Morris-Thorne sense, for it to allow information or matter to pass from one mouth to the other, the quantum state of the fields threading the wormhole must satisfy specific entanglement conditions between the two mouths. These entanglement conditions are related to the ER equals EPR connection. But the entanglement conditions that make a wormhole traversable are precisely the conditions that, according to the firewall argument, produce a high-energy barrier at the wormhole throat. The same quantum correlations that enable traversal produce prevail from the perspective of an infalling observer, a wall of high-energy quanta at the point of entry. This is the firewall problem applied to wormholes rather than black holes. And just as the firewall problem in the black hole context remains unresolved, we do not know whether the firewall is real or whether some other resolution of the paradox eliminates it. The analogous problem for wormholes is also unresolved. The honest current assessment is this: wormholes are permitted by classical general relativity. They require exotic matter that is not available from any known source in the required quantities. They are subject to stability constraints that may or may not be satisfiable, depending on the model of exotic matter. They potentially create closed time-like curves that would be destroyed by Hawking's chronology protection mechanism. And they face quantum constraints related to the firewall problem that may make traversal impossible even if the other problems are somehow solved. None of these arguments is absolutely conclusive. Each could be circumvented by some as-yet unknown physics. But taken together, they represent a formidable set of obstacles. And the direction of progress in the field has generally been toward finding more constraints rather than fewer. The Ford-Roman quantum inequality constraints on negative energy density were derived in a series of Physical Review D papers between 1991 and 2000. The key result here that the negative energy density in a region is bounded by the absolute value of T00 is less than or equal to C over L to the power of 4, where L is the length scale of the region, means that negative energy density can only be significant on very small scales. For a wormhole throat of radius r, the required exotic energy scales as r squared over g, while the available Casimir-type energy scales as much more slowly. The detailed comparison by Visser, Carr, and Dadhich in a 2003 Physical Review Letters paper showed that traversable wormholes require amounts of exotic matter comparable to the mass energy of Jupiter, concentrated in a region of Planck-scale dimensions, a combination not achievable by any known physical process. The search for traversable wormholes has not been wasted effort. Even if the conclusion is that wormholes are not physically achievable, which is not yet definitively established, but is increasingly supported by the accumulating constraints, the attempt has produced significant progress in our understanding of space-time physics. The Morris-Thorne analysis of traversable wormholes introduced the concept of exotic matter and the energy conditions in a form that is now central to discussions of singularity theorems, black hole thermodynamics, and quantum gravity. The Casimir effect, demonstrated as a result of the interest in negative energy sources for wormholes, has become one of the most precisely measured quantum mechanical phenomena and has applications in nanotechnology and precision measurement. The ER equals EPR conjecture, motivated by the wormhole entanglement connection, has become one of the most productive theoretical frameworks in quantum gravity, with implications for the information paradox, the holographic principle, and the relationship between quantum information and space-time geometry. The quantum simulation of traversable wormhole protocols on quantum computers, whatever its limitations as a demonstration of physical wormholes, has advanced the field of quantum gravity simulation and provided experimental tests of specific theoretical predictions about quantum gravitational systems. The firewall paradox, which emerged from the analysis of quantum fields in wormhole and black hole spacetimes, has generated a decade of theoretical work on the foundations of quantum gravity, and may eventually lead to the resolution of the tension between quantum mechanics and general relativity. Wormholes are not just a science fiction concept that physics has been failing to validate for 90 years. They are a theoretical laboratory, a set of thought experiments and mathematical structures that have illuminated the deepest questions about the relationship between space-time geometry, quantum mechanics, and the nature of reality. Whether a physical wormhole will ever be created, detected, or traversed is a question that cannot be answered with current physics. The honest answer is that the obstacles are severe, the available parameter space for physically realizable traversable wormholes is extraordinarily constrained, and the direction of theoretical progress has generally been toward finding more reasons why they are difficult rather than reasons why they are easy. But the question has been asked with mathematical precision, the constraints have been identified, the potential loopholes have been cataloged, and the framework for recognizing a traversable wormhole, if one were discovered, or for understanding why they cannot exist if that is the final answer, has been constructed. The mathematics says yes. The physics says not with anything we know. The final answer requires physics we do not yet have. Space has a distance between any 2 points. General relativity permits solutions in which 2 distant points are connected by a tunnel, a geometric shortcut through the fabric of space-time. The mathematics is correct. The solutions exist. The field equations permit them. Making them traversable requires exotic matter with negative energy density in quantities that quantum field theory does not permit from any known source. Making them stable requires specific properties of that exotic matter that are model-dependent and not guaranteed. Making them persist requires avoiding conversion into time machines, which Hawking's chronology protection conjecture predicts would destroy them. Making them actually passable may require resolving the firewall paradox, which remains one of the central unsolved problems in quantum gravity. The 1935 Einstein-Rosen bridge, the 1988 Morris-Thorne traversable wormhole, the 2013 ER equals EPR conjecture, the 2022 quantum processor simulation. 90 years of increasingly sophisticated analysis of the same basic question. Can space be shortcut? The answer in 2026 is, the mathematics says yes. The physics says not with anything we know, and the final word requires physics we do not yet have. The wormhole remains in the equations. It has not yet made it into the universe. One question. The ER equals EPR conjecture says that every pair of entangled particles is connected by a wormhole, a quantum wormhole, microscopic and non-traversable, but geometrically real. If this is correct, then wormholes are not exotic constructions. They are everywhere. Every entangled electron pair in every atom in your body is connected to its entanglement partner by a quantum wormhole. Does that change how you think about what a wormhole is? Drop your answer below. I want to know if the scale matters, whether a microscopic quantum wormhole feels like the same thing as a traversable tunnel through space. Next video. Why some massive stars simply vanish. No supernova, no explosion, no gamma ray burst. They are there and then they are not. The phenomenon called a failed supernova, the star N6946-BH1 that disappeared in 2009, and what direct stellar disappearance tells us about the diversity of stellar death. See you there.